and then we'll do 5.5. So Sophie asked a really good question. When you guys are doing net signed area, so again, this was from 5.4, and this very much relates to that big like final example that we did. How we, in Rohan, you asked a similar question as well too. How we find our sum depends upon the endpoint that it asks us to use, okay? Essentially, all of these sums, if you do take the limit as n goes to infinity, all of these sums should equal each other, but the formulas that we use for a specific endpoint, if they ask us for one, is as follows. So left endpoint is similar to what I did on the board right there. So that was left endpoint. So that's where the a plus k minus 1 times delta x came from. Right endpoint, there's no k minus 1. You just use that k value there. So it's just a plus k times delta x. That's the easiest one. And if I give you a problem like example 5 or example 6 on your quiz, they do take a decent amount of time because there's a lot of work to show. I would err on the side of giving you an easier form of the example, okay? And then midpoint would be a plus k minus 1/2 times change of x. So that is the formulas for how you would find each one of those, okay? And then what that does is that tells you what x sub k star is, which of course is what goes into your function right up there, okay? All right, so let's do one more example. We did example 5, and that took a lot of steps. But here's what to remind yourself of. This is very formulaic. Like none of these steps required us to do like any sort of fancy like, algebraic footwork. It was all just like dealing with coefficients and breaking apart the sums across different terms and plugging in your formulas and stuff like that. So none of them ended up being too tricky. None of those steps. There's just a lot of steps to show. Okay. So let's do another example that's similar to that, and then we'll do 5.5. Should have enough time. And again, I know it's like not common practice. I think that you guys have seen in the past where the teacher would teach a section, the next day you guys would have a quiz on it. But I feel as if this section is very simple, and I'll make sure that I review it with you guys before we take your quiz. So we'll come and review, and then we'll quiz it. So, all right, find the exact area under f of x equals 2x squared plus 10 over the interval from 0 to 2 using left endpoints. Start with n rectangles of equal width. So let's start by finding all of our things. Good place to start would be delta x. Again, that's the formula b minus a over n. So I would do 2 minus 0 over n, giving me 2 over n. And then I would do x sub k star. Now in this case, we're using left endpoints, which means we need to use this formula on the previous second slide here. Oops, let me shift that around. But we need to use this formula right here for left endpoint. So a plus k minus 1 times delta x. So my a value is 0, fortunately. That's something else that can make an example easier. And then k minus 1 times delta x. So k minus 1 times 2 over n. Okay. If you want, you could say this is 2 over n times k minus 2 over n. You can say that if you want. Change that to your input. And then now let's actually write our sum. So limit as n goes to infinity, sum of k equals 1 to n of f of this expression which we just found. Okay, so f is going to be 2 times and then 2 over n k minus 2 over n. Quantity squared, so we're going to have to square that out. And then plus 10. And then do not forget to multiply that by change in x. So 2 over n. Sorry, your file probably doesn't have this formula. I just copied and pasted it from our other slide and put it right there just to remind you guys what that formula was. Okay. All right. So now what I got to do is I got to focus on squaring out this mess. So then I would get limit as n goes to infinity, sum of k equals 1 to n of 2 times, okay, let's square. All right, so 4 over n squared k squared. And then I have 2 over nk times negative 2 over n, which is going to give me negative 4 over n squared k. But then there's 2 of them, so negative 8 over n squared k. And then plus 2 over n times 2 over n is going to give me 4 over n squared. We okay with that? And then we have plus 10 times 2 over n. All right. I don't know. I guess I would distribute a 2 to each one of these. It's a bummer because it's like it's such a simple step, but like there's so much that you have to write for it. You know what I mean? Like if I next distribute 2 to each one of those pieces, like that's just a lot. Should we make the most of our time and distribute 2 and then also 2 over n to each one of our pieces? Should we do that? That way we're not wasting any of our time. I'm going to write it right below that then because I really want to look above and reference that. So limit as n goes to infinity. Okay, sum k equals 1 to n. All right, so to all these terms on the inside, they're all going to get hit with a 2 and then also a 2 over n. So I'm just going to multiply each one of them by 4 over n. So then that first term would be 16 over n cubed times k squared minus, all right, 4 over n times negative 8 over n squared would be negative 32 over n cubed times k. And then plus 4 over n times 4 over n squared gives me 16 over n cubed. And then the 10 becomes 20 over n. Doesn't get hit with that additional 2 that's here. It only gets hit with the 2 over n from the right. Next step would be to break this into 4 different sums and the limit of all of those. So limit as n goes to infinity of, okay, I'm going to break this, like I said, into 4 sums. However, I'm going to take all of those basically coefficients and toss them in front of our sum. So like the first one is that 16 over n cubed. That's going to go in front of our sum. So 16 over n cubed, sum of k equals 1 to n of k squared, minus 32 over n cubed, sum of k equals 1 to n of k, plus 16 over n cubed times sum of k equals 1 to n of, well, there's nothing left there, so I'm just going to put a 1 there. I could have left the 16, but whatever. And then plus my final sum of k equals 1 to n of, well, I'll just put a 20 over n in front of that, and then just put a 1 in front of there. Do you follow me with that last step? Kind of mumbled it a little bit, but I saw that it was 20 over n, so I just put that in front of the sum and then left a 1 there. Okay, so I'll deal with that all in a second. Now I use my formulas. So these were the formulas that I asked you guys, hey, do you remember them? And if not, flashcards, Quizlet, I don't know, just probably, I don't even know how Quizlet works. I just know it's a thing you guys like to use, right? Although you can't use it anymore, right? Rest in peace. All right, 16 over n cubed. And then our formula for sum from k equals 1 to n of k squared is n times n plus 1 times 2n plus 1 over 6 minus 32 over n cubed times that sum, which would be n times n plus 1 over 2 plus 16 over n cubed. Okay, so the sum of 1 would just be n, because it's just 1 added together n number of times, so it's just n. And then it would be just plus 20 over n times n. Oh, baby! That's a lot. I told you guys in this step, the best thing to do is to swap your denominators. So then limit as n goes to infinity. Okay, so then the first term becomes 16 over 6. And then let's talk about this. Does anybody remember what that expansion looks like? You don't have to remember what it is exactly, but what's the degree of it going to be? N cubed, and the coefficient on it is 2. So that's really the only part that you need to remember, and you can fight through that without multiplying it all anyway. But it is 2n cubed plus 3n squared plus n over n cubed, which will help us find the limit here in a minute. Okay, and then minus 32 over 2. This would be n squared plus n over n cubed. And then plus, this would be 16 over n squared, and then plus 20. And now we are in the position to find the limit of each one of those. Okay. So for my first piece, the limit of this rectangled blue part, what is that limit going to be? 2. So then I have 16 over 6 times 2, which is just going to give me 16 over 3. Minus, what about this clouded blue piece right there? It's going to be 0, because you have a higher degree in the denominator than our numerator. So then that's just going to terminate to 0. So minus 0. Plus, what about, I'm running out of shapes, my triangle. 0 as well. And then, ooh, I don't need a shape for the last one. I get 20. So then 16 over 3 plus 20 is going to give me 76 over 3 is my area. Okay? All right. I did that way more efficient than I did at first period. First period, I feel like I did it in a very awkward way. But, okay. All right, questions there? That's the end of 5.4. Let's do 5.5. It won't take us long to cover 5.5. Should be pretty simple. Again, I believe that this is, of the 5 sections that we've covered so far in Chapter 5, this will be the easiest. I think first period agreed. Tessa, did first period agree? They just weren't happy with me. They're stressed out right now. Yeah, you guys. Sounds like you guys have a lot of tests this week, like physics and stuff.
We do.
What's your deal? Where are you going?
I'm going to Arizona Thursday, Friday.
For what?
We have a physics test.
Friday.
Bro. Oh, you were.
Quiz tomorrow.
I'm missing.
Quiz tomorrow. Test Friday. Sorry.
Wait, he said that we're likely not getting to the physics
It's
test
also
till
tax.
like next week.
Well, I don't know. They were talking about the hardest test in the whole.
No, yeah, he said it.
He's not here.
We'll get you there, bud.
Wait, no.
We'll get you there.
Who's saying that? They're wrong. We're not.
All right.
He said we're getting to that test tomorrow.
I got you guys derailed. That's my fault. Here we
We're
go.
not getting to till next week. If like.
Oh yeah, you guys were not in here yet. Quiz tomorrow. Test Friday.
No. Why are we?
No.
What? No, not this class. God. Ah! All right, here we go.
Hardest thing we're ever gonna learn in class.
Hey, so we did indefinite integrals already. We called them antiderivatives in the past. That is what you guys did in like section 5.1, just like super basic antiderivatives. Or it was 5.2. But either way, then that's when we had that like tall, skinny S, and we did like U substitution after that in 5.3. We're going to come back to that, but we're going to build that notion a little more compared to what we're going to talk about in the next part of Chapter 5. So we're going to do more Chapter 5 stuff like after this test on Friday, but I break Chapter 5 up into 2 tests because there's just so much stuff in Chapter 5 that it behooves itself to break it into 2. All right. Hey, I found out how to like enclose things. So I I'm going to try to work on enclosing our definitions and like, I don't know if I'll choose like a red Elmo theme every time. It reminds me of Elmo. But I'll try to box in like your important like definitions and theorems and stuff like that. No problem. Remember how we handled area in the past? We did it in like that problem that I went over on the board and then the one that I did at the end of 5.4 just now. So now we're going to update our definition of what is called net signed area. Okay. So if a function is continuous on a closed interval a to b, then it is integrable. And the net signed area between the graph of f and the interval a to b is as follows. This definition is from Friday, so that's not new. The new part of your definition is right here. Okay, so we see our integral symbol there. But notice there are values attached to that symbol. What that means is we want to find the antiderivative of our function, but then we are going to work over the interval from a to b, okay? So what that tells us, I mean, this told us, like the underlined part, told us our area under a curve before. So what I'm telling you is this notation means the same thing. It's just way easier to write. So instead we do the integral from a to b of f of x dx, okay? So we call the right side, this is what's called a definite integral. When you have an integral that has limits attached to it or numbers attached to it, that's called a definite integral. And the numbers a and b are called, so a is your lower limit of integration and b is your upper limit. So I'm going to call them lower limits and upper limits, okay, respectively. Yeah. Okay, so let's rewrite what would have been a problem that we would have done in yesterday or Friday's homework or whatever. Let's actually write that as a definite integral instead. Okay, so they'll give you an interval from 0 to 4. That represents my limits of integration. So lower limit to upper limit would be from 0 to 4. So this is the integral from 0 to 4 of, and then we got to come up with our function. That very much just relates to our rule. And essentially what we're going to do is we're going to replace our x sub k stars with just x. So it becomes 6x times quantity 4 minus x quantity squared. But then don't forget that delta x is there, so that becomes our dx. And that's it. That's what I want you to do, is just write it as that, okay? All right, so let's think about what that means in terms of net signed area, okay? And I want to have a discussion about area because previously on mathematics, you guys have always viewed area as something that is positive. And I slightly introduced the notion that we can have negative area, okay? What you need to think about it as, like, let's build this notion this way. We approximated area by using rectangles initially. So we did base times height. So our base was generated by the difference in our x values, and then our height was just generated by the height of our function. But our function can dip below the x-axis. So because of that, that would give us negative heights. Now, also think about it in terms of like, okay, well, Mr. Pacifico, how is that even practical at all? Think about it in terms of when we did like velocity, like position, velocity, and acceleration. So what did it mean for us to have negative velocity? That meant that our particle that was bound to an x-axis was moving where? Yeah, left, or in other applications, it's like down, like in some sort of negative direction. So then when we take our integral, let's talk about what this means. So if we think about the idea of like s of t, and then the derivative of that would be v of t, and then the derivative of that would be a of t. To go down, you would take your derivative, right? If I wanted to go up, I would instead need to take my antiderivative or my integral, right? Which means if I take the integral of my velocity, for example, what that's going to tell me is my position. But if you think about like what the antiderivative has meant to us, it's been area under the curve, which we're going to find out means the amount of something. Area tells us the amount of something in a space. So if I integrate my velocity, what that tells me is the amount of distance that I've traveled, okay? But if I'm traveling in a negative direction, that would give me a negative area, okay? So that's one application of how you can think about negative area. The other thing you can think about it is like let's say you have like liquid in a container, and I'm giving you the rate at which it's going out. So if liquid is leaking from this like container or whatever, our final value is going to be less than our initial value, right? So then that's a negative net change, or we would say a negative net area. So that's why you can have areas that are negative. So like, for example, if I have this graph here, let's just say it's whatever from A to B, and we like broke it up into intervals and stuff. You know, we would approximate this by using a bunch of different rectangles. And essentially, I would have a positive area. And then I would also have a, if I do this, more rectangles. Whether I choose them by left endpoint or right endpoint doesn't really matter. But I would also have a negative area as well too, okay? So then essentially our area above our axis, if we subtract that from our area below our axis, that'll tell us our net signed area, okay? Now you'll find that that usually shakes out in such a way that you guys don't need to be too cognizant of it. But in this section, we're going to look particularly at how to find those areas, okay? And again, net signed area is just represented by the integral from a to b of f of x dx, okay? So when you see that in this section, what that means is, hey, find the area under the curve of that function, okay? Now, I think in retrospect, I was a little kinder when making this set of notes than I should have been, because I gave you the graphs for each one of these. I should have had you guys graph these out. But anyway, let's find the areas using our geometric formulas. Okay, so what we're going to do is we're going to focus on finding area solely from what we know about symmetry and geometry. All right, so the first one is area under the curve between the x values from 1 to 6 of 2 dx. So 2 is just a horizontal line. If I kind of complete my picture here, we're working from 1 to 6. So we want to find the area between the curve and the interval of that value right there. What shape is that? Yeah, it is. So all I want to do is just find the area of a rectangle. What's the area of a rectangle? Very good. So then my area is going to be my base, which we're just going to go along our x values, subtract those. So let's say 6 minus 1. And then times our height, which is just going to be 2. So very simply giving me an area of 10 units squared. All right, let's look at the next one. I'm going to find the area between the curve of x plus 2 over the interval of -1 to 2. So we're going to say -1 is here, 2 is there. So it's going to look something like this. What shape is that? It is indeed a trapezoid. Do we remember the area of a trapezoid? That's exactly what it is. I write it like this, though. I put the 1/2 out in front. So 1/2 base 1 plus base 2 times our height. Good. Now, when we think about trapezoids, which are actually going to come up a ton in this course, so buckle up for that. I usually think about it in terms of like a rotation. So I usually like to rotate mine so that it looks something more like that. Okay. So then the height of your rectangle is actually given by your difference in your x values. And your base 1 and base 2 come from the heights of your function. So come from your f of x values. All right, so if I do that, area equals 1/2 integral, oh no, whoops, that's my bad. All right, so then I would do base 1 plus base 2. So we need to find the height at this value and then the height at that value. So if I plug in -1 to my function, I just get that that height is 1. And if I plug in 2 into my function, I would just get that that height is 4. So then that represents my base 1 and base 2. So then I would have 1 plus 4. And then the height of my trapezoid itself is actually the difference in my x values here. So 2 minus -1. So 1/2 times 5 times 3 gives me 15 over 2 units squared. Let's do the last one on this slide, and then there's many more. All right, so, integral from 1 to 3 of 2 minus 3x. Okay, so 1 is like here, because if we plug in 1, 2 minus 3 is going to give us -1. So then that's actually like this value here. And then 3, I don't know, let's just say that's like here. It gives us this value down here. So then this would be 3. If I plug in 3, I get -7. And if I plug in 1, I would get -1. So this is 1, -1. Hello. I don't know what happened there. And then, okay, so that's our area. What are some things you can tell me about my area? Still trapezoid. Anything else you can tell me about my area? It's going to be negative because it's below my x-axis. Okay. Now, if we think about rotating this, you know, we could imagine it looks something like this. All right. So let's like pick apart what our heights and bases are and stuff like that. Okay. Now, if my, oh my gosh, can I do this? Well, can I like duplicate? Oh. And then can I rotate that? Please let me rotate you.
Yeah, it's press resize.
For real life?
Yes, for
And then, that's so exciting. Okay. So then if I think about like my values, it's just the same thing that I drew. I don't know why I'm getting so excited. All right, so the height of that rectangle in this case is actually going to be positive, right? Because it's just my change in my x values, so that's going to be a 2. But my base 1 and base 2 are actually going to be negative because they go down, okay? So this one, let's say, is -1. And then this one, let's say, is -7, okay? All right, so let's find our area. Area equals 1/2. All right, so base 1 plus base 2 is going to be -1 plus -7. And then my height of that is going to be 2. All right, so then you would get 1/2 times -8 times 2, which gives me -8 units squared. Okay. All right, questions there? Okay, cool. We have many more to do. More. Orange. Orange.
Are you going to give us the graph of the quiz? Or do you have to make one?
You'd have to make your own.
Wait, this is what we use tomorrow?
Mhm.
Okay. Do you use the graphs to figure it out?
Mm.
As long as you know what shape it makes.
It's a good idea to sketch it.
Okay.
So that's why I said I almost wish as if I would have. Let's just do this. Oh, wait, you guys have it in front of your face. Darn it. You guys know how to sketch linear functions, though.
This one right here.
What? What one?
I may have forgotten. The circle.
Do you guys remember that square root is semicircle? Good thing to know. So square root of r squared minus x squared just represents a semicircle. So, yeah. All right. So let's do the first one. Okay. So integral from 0 to 2. We got to be careful about that. Okay. One thing you have to keep in mind is that your area is bounded by your function in the x-axis. So if I look at my first ones from 0 to 2, that's going to represent the area of this triangle, and then also the area of the triangle that's formed once you get to 2. So that's these two areas. What are your thoughts? Maybe we should split this into 2. 1/2 base times height plus 1/2 base times height. But do you have any early predictions? Yeah. So if they're both the same, but one is positive and one is negative, it should just be 0, right? Let's chase that through real quick. So 1/2 base of my first triangle is 1 minus 0. My height is -1. Plus 1/2 base of my second triangle is 2 minus 1. Times a height of +1. So -1/2 plus +1/2 is a net change of 0 units squared. Okay. All right. Tessa was bummed out about the semicircle, so let's look at that one. All right. So again, square root of a value minus x squared tells you a circle of with a specific radius. So the square root of 16 is what my radius is going to be. So my area, what's my area equation for semicircle? Okay, and then my radius is just going to be 4. So then I would just get my area is equal to 1/2 pi times 4 squared, or 8 pi. Unit squared. Take off a half point if you don't write that. Or maybe a full point, depending on what kind of mood I'm in.
That reminds me of the quiz. I was almost done. I went back to plus C for all of them.
Yeah, you better have. You better have.
Thank you, everybody.
Miss Gillette told me her joke about that. She said that if you don't write plus C, then you are leaving off an infinite number of solutions. So you better hope I don't take off an infinite number of points.
I got a negative.
That's what Miss Gillette said her joke was,
Plus C.
which honestly is sensational.
But then I erased it because it looks like C plus.
I did not.
And I didn't want to get that.
Substitute you out of it?
Yeah, I did that. And then what?
All right, here we go. Let's do these. This first one's pretty basic. I don't think it's too bad. Shh. All right. So our first is just going to be another rectangle. Yeah. So tell me about my area. Base times height, it's just a rectangle. So integral from -4 to -1 of -5 dx is going to equal. All right, so my base is going to be -1 minus -4 times my height of -5. So then I would get 3 times -5, so -15 units squared. That's a good question. So those are my limits, right? -1.
Yeah, I just don't.
Instead of what? Just writing 3?
Or is that just like, is that just for the interval?
It was on.
That's
It was
just
on
it.
this. Okay, I'm sorry, everybody.
Can you like show the verbal
Yeah,
line?
wait, yeah. Is that SC? Negative 5.
I had some illness in the family.
Again.
It wasn't my kids this time.
It's that time
Was
of
it
year.
No, it wasn't me either.
Okay, well, this is.
But
Everybody asking personal
yeah, it's more to the situation I'd rather not talk about. So, all right, let's go and do the next one. So,
I'm a super specific. I have a question.
yeah.
If the base and the height are both negative, how is a negative answer?
Our base is going to be positive because we're doing it from left to right.
What?
Or we're subtracting our right value, -1, from our left value.
Oh, okay.
So it ends up being positive. Is it clicking now? There could be. I'll briefly touch on that today.
Is this the second?
Why?
We're gonna give you a new tip.
That's why it typically ends up being positive. Yes, unless we choose our limits in a weird way. I'll show you in a few minutes. All right. -2 to 2. We should break this into 2 intervals. So let's do here, this triangle, and then this triangle. Let's find the area of each one of those. So then we're going to add together the area of 2 triangles, okay? So we're going to do area equals 1/2 base times height plus 1/2 base times height. Okay, so then we would get 1/2. Do I need to find some values here? No, I think it's pretty obvious, right? This is 1, and then the rest of the values are pretty obvious. And then this is -1. So -2, -1. Okay, so then the base of my first one would be negative 1 minus negative 2 times my height of negative 2 plus 1/2 times my base of 2 minus negative 1 times my height of 2. So giving me, this first one would be negative 1. Did I do that right? Wouldn't it be negative 1/2? Hold on. Oh, because that's... Oh, this is negative 1 right here. I'm sorry. That's negative 1 right there. That's my bad. Sorry, this last value right here should be a height of negative 1, not negative 2. It's my bad. All right, and then the next one, so it would be 3/2. Is that right? No, just 3. It's just 3. So then 5/2 units squared. Bless you. I want you to notice something, though. Essentially, we broke this area into 2 separate areas, and then we added each one of them together. So if we used our integral notation, we basically said that, let's actually move this over here, the integral from negative 2 to 2 of, we just called it f of x dx, is equal to the integral from negative 2 to negative 1 of f of x dx plus the integral from negative 1 to 2 of f of x dx. Do you guys see that? That like those individual integrals just represent the area of each one of those triangles that I just found? Okay. So that is a property of our integrals that we're going to learn on the next page, which basically says if you have a c value that's in between these values here, you can break your integral up into 2 separate integrals by changing those limits. Okay. Now, we'll find that that also applies if your value is not between those values, and then that's how you would end up with a negative base instead. So let's look at these properties, okay? So these are properties of definite integrals. I think, so it says definition 5.5.3. I think that's like, I think it's only 2 of them. So I think it's like these 2, maybe? That's 5.5.3. The rest of them are just like different theorems that are in your textbook, but I just put it all in the one location, okay? We've seen the first one before. The integral from a to a of f of x dx is just 0 because our base isn't changing at all, so that area is just going to be 0. And then the next one tells you the integral from b to a, instead of a to b, the integral from b to a of f of x dx equals negative the integral from a to b of f of x dx. So you can change your upper and lower limit at a consequence of putting a negative in front of your integral. Because if you think about, like, if we found the difference between a and b, if, you know, b was to the right of a and we did a minus b, that would give us a negative value. So then instead I could switch it and put that negative in front, okay? That third property is what I just talked about on the last slide. So the integral from a to b of f of x dx equals the integral from a to c of f of x dx plus the integral from c to b of f of x dx. I showed you an example where c was between those two, which is typically what the case is, but it doesn't have to be. C does not have to be between those two integrals, okay? And it'll still work out to be the same because the negatives will end up canceling out, okay? The fourth property should not surprise you. If you have a scalar multiple times your function, you can just pull that in front of your integral. We did the same thing with sums. We did the same, which is what an integral is built on, is a sum. We did the same thing with derivatives as well, okay? If you're taking the integral of multiple functions or terms added or subtracted from each other, they can each get an individual integral. We'll use that one a lot, okay? And shoot, you guys have used that one before, just not with limits on it. Okay, the next one's pretty good. If your function is integrable and non-negative, also, for it to be integrable, it just needs to be continuous. And if it's non-negative, then the integral from a to b of f of x dx is going to be positive. So you have a positive area if your function is always above the x-axis or touching the x-axis. And if you have two functions that are integrable and f is less than g, then the area under the curve from a to b of f is going to be less than the area under the curve from a to b of g. Okay, so these are properties of integrals that you guys can use to find some values pretty quickly. Let's do these here. I meant to put another example in here on this page, but I just didn't copy and paste it. So we're just gonna have to make one up on our own. But we're smart and resilient, so we can do it. All right, so first one, integral from 0 to 6 of f of x dx. Well, if I look up above, we're gonna treat these as reference values here. So I know the integral under the curve from 0 to 3 and the integral under the curve from 3 to 6, okay? So if I want 0 to 6, I need to do what? Add them together. So it'd be the integral from 0 to 3 of f of x dx. Sorry, let's write that in blue because I underlined it in blue. And then plus the integral from 3 to 6 of f of x dx, which is just going to give me 4 plus negative 1, giving me a value of 3. What do I have to do for the next one? Yeah, swap them limits, right? So negative in front of my integral, and then it goes from 3 to 6 of f of x dx. So negative, and then that is negative 1, so I get positive 1 as my value. What about C? I don't really feel like showing any work to that. It's just going to be 0 according to our properties. What about D? Boot that negative 5 out, right? And then integral from 3 to 6 of f of x dx equals negative 5 times negative 1, giving me a value of 5. Okay? I'm not putting units squared on each one of those, okay? Your integral represents your area, but since it didn't specifically ask for an area, and it just asked for the value of that integral, I'm not going to put a unit with it, okay? But if I say, like, hey, find the area, those you need to put units squared on, okay? Hey, I'm going to make one up below. So bear with me here. I had a really good example that I used in the past, but let's just do something like this. I don't know. And then let's make like a nice linear piecewise function here. No, I don't like that. That's not straight enough. Two. Actually, no, we're going to put a tick mark here, and then also here, and then there. That's what we'll do. And then we'll say this is negative 3. So 1, 2, 3, 4, 5. All right, there's our function. Here's the things I want you guys to find. Let's do the integral from 0 to 1. Let's call this f of x of f of x dx. We'll do the integral from 1 to 3 of f of x dx. And then we'll do the integral from 3 to... Well, let's just do 3 to 4, and we'll just fight our way through it. Of f of x dx. And then we'll do the integral from 4 to 5. F of x dx. And then, as a bonus, we'll do the integral from 0 to 5. Fx dx. C is going to give us problems, but that's okay. We'll get there. I'll have to amend my picture likely. We'll say that this is 3.5. So we'll say that x-intercept is 3.5. Although it's not going to be 3.5, would it? Nah, it's okay. Whatever. We'll say it's 3.5. Okay. let's go through and find each one of these values. Okay, so integral from 0 to 1 of f of x dx. What am I doing? Triangle, right? So that's this part right here. Okay, so 1/2 times my base of 1 times my height of 2, giving me an area of 1. And then let's do 1 to 3. So then we're doing a rectangle, yeah? Okay. All right, so then in that case, we would just do base times height. So 3 minus 1 times my height of 2, giving me 4. All right. Here's what I'm going to do, actually. I'm going to change this value of -3. I'm going to change it to -2. That way it hits that value, and I don't have to worry about it. I'm just going to say, because then it actually hits at 3.5. Okay, so then what would my area under the curve from 3 to 4 be? Be this area, and then that area. What should happen there? It should cancel out, and it should be 0, right? So I can show that, and it would look like this. So 1/2 times my base of 1/2 times my height of 2 plus 1/2 times my base of 1/2 times my height of -2. But that is just going to equal 0. And then let's do my last one. All right, so that's from 4 to 5. So there. All right, so that's just going to be another triangle. 1/2 times my base of 1, 5 minus 4, times my height of -2. So that would give me -1. What do I want to do if I want to find the area under the curve from 0 to 5? Add them all together. So then I would just get, what was my first one? 1. So 1 plus 4 plus 0 plus -1. So my area under the curve would be 4. My net change. Okay? Think about it this way. If this represented velocity, so let's say f of x was actually my velocity function, v of t, whatever, I would start by going to the right. So going in a positive direction, right? So I'd start by moving in a positive direction, and then constant velocity. And then my acceleration would change. And then at 3.5, I would then start moving in a negative direction, okay? And then eventually I would go back towards a positive at the end of the interval. But, you know, I go as far as whatever the area under the curve from 0 to 3.5 is, but then I start turning around and going in a negative direction. So though there's more of my positive movement forward than negative movement forward, I'm still going to end up with a positive displacement. Okay. Eventually, we'll talk about the difference between displacement and total distance traveled, but we'll get there. All right, so your homework is 11 through 26. So again, as a recap, tomorrow we will go over 5.5 homework. So make sure you do it in a way that is quality. I would say ones to focus on in that homework would be like, particularly like 11 through 18, and then also like 23 would be good ones, I believe. So do this. Tomorrow we'll go over it. I'll make sure we spend the time to go over it, and then I'll give you the last part of that class period to do your quiz. It's also over 5.4, so review stuff about summations. And then you'll have the rest of that to work on your chapter review. And then Thursday, we'll come in, we'll review our chapter review, and then Friday, you guys will take your test. Sorry it was all jam-packed. It would have been better if I would have told you guys yesterday, I know. But life is the way life is sometimes.
How many points was the quiz yesterday?
I haven't graded it yet. How much do you want it to be worth?
How many? Just no quiz.
I don't know. I don't know. This is